Hey guys, welcome back. In this video, I want to talk about the channel estimation in case of multi-user MIMO. Okay, and I want to talk about all the relevant concepts so that the multi-user MIMO concept is understood well. So, to begin with, I will start with the SISO. Okay, because we have seen the channel estimation for SISO in the beginning, and then we had moved to MIMO. So it is easy for me to relate the concept with the SISO. So in case of SISO, let's say we had one UV, okay, and it has got just one antenna, and let's say I have got the base station and I've got one antenna, okay. So in this case, we are clear about one thing, that is DMRS allocations or your pilot allocations, right? And to perform the channel estimation, what do we do? Like we have single equation y is equal to hx plus n, and we know already how to perform the channel estimation. I will not go through that, but you can watch previous videos for that. But it is pretty much straightforward, right? Now, when I say single antenna at the transmitter side, okay, from the UV, which means that we can support one layer, right? So when you're dealing with one layer, let's say you transmitted, the data x1, then you need here minimum one receive antenna, okay, RX antenna to get back this x1, to decode x1 successfully, right? This is one of the scenarios we have. So to understand the multi-user MIMO advantage, what we need to look at is, let's say, the data rate. Okay, so for now what I will do, that we have the grid, okay, OFDM grid, which we usually talk about, OFDM grid, which is of one slot worth. But right now what I will consider is entire I mean across one symbol we have got, let's say, 100, sorry, yeah, uh, I will just say, okay, 100 subcarriers. Okay, let's say for example I will just take 10 symbols. So what is the data rate? All other factors I will just consider it as one to calculate the data rate. Okay, to make it simple, we have 100 subcarriers into we have just one layer or one antenna. So then we have 10 symbols. So let's say 1000 I will say bits per second. Okay, all other factors like code rate, number of bits, and many other things I've just taken it as one. Okay, Mm, so this is the data rate achieved. Now let's say I will consider the scenario where we have the two UVs. Okay, um, so I have the base station. Okay, base station also just as one. So now the thing is, first UV, second UV, both have got one antenna and both are dealing with one layer. Okay, now if we want to support this multiple UV from this base station, how would we allocate the resources? Okay, so again, if I take the OFDM grid, and I was talking about 100 subcarriers, definitely we need to divide this 100 subcarriers, 50 subcarriers to one UV, 50 subcarriers to another UV, so that they are having orthogonal with respect to the frequency domain allocations, right? So in this case, each UV, how much data rate we would have? So which is 500 bits per second, which is 50%, right? What we saw earlier. Okay. In this case, how about the DMRS? Since anyway they are separated in terms of frequency domain resources. Let's say if we have the DMRS, then for first UV the DMRS can be allocated here, and for the second UV the DMRS will be allocated on a different frequency domain resources. Both of them can be given same port 0. This also port 0. What I mean to say is that um, both of them can go for similar kind of allocations, that is, so the first subcarrier is transmitted D1, D2, like that. Okay, this is, let's say, port 0 configuration as per 3GPP spec. Similarly, for the second UV as well, okay, same thing can be done. Okay, this is for the second UV. So here also I can go for D1, D2, similar kind of configuration. Okay, So no problem here, they are separated in terms of frequency domain resources. So here everything is fine with respect to DMRS allocations. So the another thing what we need to note down here is at the base station, the receive antenna we need just one. Okay, so we are dealing with only one layer. Here one antenna would be sufficient for decoding both UV's single antenna data. Okay, but now let's say, um, okay, I want to talk about one more aspect, that is after the channel estimation. Okay, we understood how DMRS allocations are happening. Okay, then we also know, okay, channel estimation, for this particular, for this particular DMRS, we can perform y is equal to HD1 plus n, right? We can perform channel estimation separately for this UV, and this, separately the channel estimation can be done for UV number 2. Okay, so here there is a single equation to be decoded. Here also there is a single equation which needs to be decoded to get back the channel estimation. Once the channel estimations are done, then we can use those channel estimates h at to use in y is equal to h. Let's say here I transmitted x1, here I transmitted x2 from there. So let's say for the first TV I have transmitted x1. I can use this channel estimation h at. Okay, so h at inverse y is equal to x1 plus n, or basically how do we decode this x1 using, as I was telling in the other series, we will, let's say we go for MMSE IRC. In this case, since there is only single equation, it will just boil down to something like, there is no matrix inversion. You will have one cross one inversion into something, so it will be just like a scalar division. Okay, so I hope you got the clarity. Even in this case as well, DMRS allocations are clear. You also got to know how to perform the channel estimation, and even MMSE is also similar to what I just mentioned. It's all fine. Now what I want to mention here is, let's say now I will go to single UV. Okay, one UV but two layers. Okay, before that, what I want to say here is, at the RX side, I was mentioning we have one antenna. Okay, and here basically I was telling the minimum one RX antenna. What if I had two antennas here? Okay, let's say what if I had two antennas? Then in this case, so you will have H bar, which is 2 cross 1, right? So now what will you have? Y bar is equal to H bar X plus, we can say this is, since this is X1, so we can say something like this. So using this X1, I mean to say, let's say if this is a DMRS, then we can get back channel estimation H bar. There is no problem, we can get it easily, right? This also we had seen, this is also coming under single input but multiple output case, right? So but once we get this, okay, how to do the IRC MMSC. So since this channel H bar is 2 cross 1, then we also have H bar Hermitian. This will become 1 cross 2. Basically, your matrix inversion becomes 2 cross 2. Okay. Okay. So basically, this will try to give the receive diversity. So I hope this one is clear. Okay, this can be when there is only one layer from transmitted from the UV. At the receiver, we need one minimum one RX antenna, but it can be more than that. For now, for example, I just taken two receive antennas. I mean, in which case we will have receiver diversity. Okay, and channel estimation will be simpler, and as well as even MMSE IRC becomes a little bit more time consuming because of 2 cross 2 matrix inversions. So now when a single UV has two layers of data to transmit, then at the receiver side, what is the requirement of antenna? Okay, here minimum I need two receive antennas. Okay, so one antenna will not work out, two antennas are required. So then what would be my channel matrix H? It would be 2 cross 2, right? So in this case, two layers, we had seen a MIMO channel estimation, right? How to allocate the DMRS, right? So we had seen a couple of techniques, two scenarios we had seen as of today. um, Say let's say this is antenna 1 and this is antenna 2. Okay, so in this case what happens? So this is d1 d2 and I can go for d1 and d2. So this would give sufficient orthogonality in terms of allocations, because two layers means the data present on layer 1 and layer 2 are occupying the complete 100 subcarriers. Okay, so if I take the OFDM grid, okay, in the 100 subcarriers, so we will have one more OFDM grid for antenna 2. Okay, this is antenna 1 and this is for antenna 2. Again I have 100 subcarriers. Okay, so total, what is my 100 into 10 into 2 layers, which is becoming 2 on 2000 bits per second. So compared to the previous case, we have double the data rate, right? In case of two layers. But even though we had, the data occupied on complete 100 subcarriers, when it received at the receiver antenna, these two antenna 1 data and antenna 2 data were interfering at each other at both the receiver antenna Y1 and Y2. But um, we had we had this scheme of allocating the DMRS on orthogonal subcarriers so that it facilitates to perform the channel estimation accurately, and it ensures that the feasibility of channel estimation is possible, right? And by using the later on by using the MMSE IRC, in this case we need again 2 cross 2 matrix inversions. By using MMSE IRC, we are able to get back the data what is transmitted. Okay, so I will just write, we will be able to get back x bar at, which will be x1 x2. Okay, antenna 1 data, antenna 2 data, we will be able to separate it out. Okay, now I am entering to multi-user MIMO, because see what happened in this case is that when I had taken multiple UV, each having one layer, here here how did we actually transmit? Okay, here I mentioned that we have to divide this 100 subcarrier into 50 subcarrier, 50 subcarrier, but definitely at each UV we will have the OFDM grid, right? So for better clarity I will write the OFDM grid across each UV. So in this case, first UV, let's say this is the 50 subcarriers is allocated, the remainings are empty. Okay, zeros. Similarly for UV number 2, this is the OFDM grid. The top portion 50 subcarriers are allocated, whereas the bottoms are all zeros. Okay, that is how it is transmitted. But when it reached at RX, that's how it was looking like. Okay, then we know that we could easily separate out to these two. We were doing the channel estimation MMSE IRC for UV wise in this case. Okay, so the question here is, why can't UV number 1 and UV number 2 go for full subcarrier allocations? Okay, and get 1000 bits per second for UV2 and 1000 bits per second UV number 1. Okay, that particular thought was appeared based on, I would say, two layer concept, because in two layers we are able to transmit x1 and x2 on complete 100 subcarriers and we are able to get 2000 bits per second, right? So Why can't I divide? Let's say in this case, even though this is a single UV, which has got two antennas, I would just, let's say, divide this and say this is one UV, and the second one is this is another UV. This is UV number one having one antenna, another UV having another antenna. So if we treat at the RX side, if we treat the two UV single antenna case as a single UV to RX, then we will be able to achieve better data rate, right? So that's where this multi-user MIMO concept came into picture. But definitely, have have I mean, to have multiple UVs clubbed together at the receiver side, we need two receive antenna. Okay, that is the minimum criteria. What I mean to say here is, like in this particular case, we had one UV, one antenna, two UV, one antenna, second UV, one antenna. So since both of them were operating at one layer and the resources were divided in frequency at the base station, we required just one antenna. But if you want to utilize first antenna and second antenna for the complete full subcarriers, and if you want to treat this entire thing like a single UV two layer, then definitely at the base station we need to have two antennas. Okay, so similar to this one, two layers, we need minimum two RX antenna. That's why at the base station, to support multi-user MIMO, where the allocations are completely overlapping, then we need two receive antennas. So that's where I will write it over here, that first UV, second UV, single antenna. So then definitely, in if both of them are paired and we are operating both of them as multi-user MIMO, okay, in this case, then definitely at the base station we need two receive antennas. Now the receiver would be treating, even though these two are separate UVs, at the receiver side we would be treating it as single UV two layer. Okay, that's why we needed two antenna here. So now in this case, how would be the allocation? How would be the DMRS allocation? So similar to what we spoke in case of two layer, right? Okay, so we can go for, this is one kind of allocation, or otherwise another allocation is, as I was telling, the frequency domain OCC has been discussed, right? So we can go for such a kind of allocation. Let's say D1 D2 for one UV, then for the another UV, what you can do is, if you want to use same D1 and D2, you need to have that OCC. Okay, 1 and minus 1 is multiplied to the other UV. So in this case, first UV should go for port 0, let's say. In this case, this will be port 3. Okay. But whereas in the earlier case, when we had two UVs but resources are divided in the frequency domain, we were going for same port. Okay. But if we want to use this as a multi-user MIMO, then we need to have a different port. We should ensure that both UVs are assigned with a different port, such a way that they have orthogonality. Okay, because this should facilitate the proper channel estimation. Now, how does the channel estimation happens in case of multi-user MIMO? So here we should be clubbing, right? Because we are treating it as single UV two layer. Definitely, then what will happen? H 2 cross 2. Okay, but if I take H, okay, H12, H21, H22, so if you clearly see, because my matrix will become, okay, this is what, sorry, this is x1. Okay, in the other case, if I'm using the time domain OCC, then it will become something like this. All right, so in this case, This column corresponds to UV number 1, or let's say whichever has been assigned with port 0. The other column corresponds to UV number 2, which corresponds to port number 3. That's how we will know, actually, based on port allocation for the DMRS. That's how we will know that which column belongs to which UV, and basically, uh, the other column would belong to other UV. Okay, so now this kind of channel estimation we already saw, right? We saw, in this case we saw frequency domain OCC, because this is now similar to 1UV 2 layer case. Okay, MIMO channel estimation we have seen. Only thing is that we are clubbing the channels of these two UVs, and we are going to perform the channel estimation. Here we cannot do UV wise channel estimation. Okay, like the way we did it here. I was mentioning here that for UV1 we can do the channel estimation separately. For UV2 we can do the channel estimation separately, and then MMSE IRC also we can do separately for these two UVs. But in this case, we have to perform in one shot, and then MMSE IRC we need to apply, and we would be applying considering this consolidated channel for these two paired UVs. So definitely, we will get X bar at directly. Okay, after performing MMSE weights here, 2 cross 2 matrix inversion we will be doing. Now this one will have x1 and x2. Okay, now we know, because the first column corresponds to UV1 port 0, so UV1 port 0's data is here. The first one will belong to x1 will belong to UV1 port 0 data, second one belongs to UV2 port 3 data. That's how after this we can segregate, because we will know which data corresponds to which UV. So I hope you got the clarity, how to perform, first of all, MIMO channel estimation, and even how to decode the data, how the algorithms are getting changed. Basically, I hope you got to know that. In summary, if I want to tell, if you don't go for multi-user MIMO, okay, I'll put cross mark. Then you can perform channel estimation and MMSE, UV wise. Okay, but let's say if you are going for multi-user MIMO, then for the paired UVs, definitely you have to have a combined channel estimation for all the paired UVs, and accordingly even MMSE also you have to uh, perform in a combined fashion. So there will be a difference in the algorithm for channel estimation and MMSE if there is a multi-user MIMO concept. So with this, I think you got the clarity, like you got the clarity on what algorithm changes are required for multi-user MIMO, how DMRS allocations will happen, how the data rate has been increased in case of multi-user MIMO. Basically that will tell the advantages in terms of achieving higher data in case of multi-user MIMO, and you also got to know how you would perform your MMSE channel estimation, sorry, MMSE equalizer. So to get more clarity here, what I would do is in the next video, I will take up the example of multi-user MIMO of two UVs, each having 2 layers. Okay, that would be a little bit more complex, but we will try to analyze that to get better clarity from this one UV single layer case. Okay, thank you very much. Have a great day. Bye bye. If you're looking for more videos, please do subscribe to the channel.